academy will make announcement, detailed announcement regarding the exam soon, maybe sometime this week or earlier next week, so that students are aware of the rules and regulations for the exam. All right. Okay, let's continue with the lecture on the frequency response. Okay, let me make it as slideshow. Okay. And I put a pointer here. Pointer. Oh, it's okay. Do you see my pointer? Okay.
Yes.
All right. For this chapter, the frequency response, it will cover the transfer functions. This chapter will introduce the idea of the transfer function, which is the means of describing the relationship between input and output of a system. So in this, the system that we are interested in is the circuit systems. And from the transfer functions, we can always plot a body plot or do a graph of body plot. And the important about the body plot is that it is used, body plots and their utility in describing the frequency response of a circuit will be introduced in this chapter, and the concept of resonance as applied to LRC circuits will be covered as well. Okay, remember last semester we learned about first order system and second order system. Recall that a first order system consists of two components, right? We have if the circuit is composed of resistors and capacitors, or if the circuit is composed of resistors and inductor, both will be first order system. But if the circuit has all three components, the resistors, capacitor and inductor, it will make a second order system. Okay, and from this system, actually you can represent the system as input and output, and you can represent the system in terms of its transfer function. Given an input and then you have an output, so that the black box is in the middle. So what is the transfer function of the system? So from the transfer function, you can actually plot the response, the frequency response of the system, because when you have first and second order, you have waveform where it is actually systemic systems. Okay, and from this RLC circuit, we will have behavior of filters. Frequencies can be filtered, and from that we will also discuss on types of filter circuits. Okay, the frequency response is actually the variation in a circuit's behavior with change in the signal frequency. This is significant for applications involving filters, and filters play critical roles in blocking or passing specific frequencies or range of frequencies. Without the filters, it would be impossible to have multiple channels of data in your radio communication. So we have in a raw signals, there will be noise. So with the filters, you can remove the noise. You know the frequency of the noise, so you remove the frequencies of the noise. Okay, that is the basic of frequency response. Okay, so let's recall from semester 1, when you learn DC circuits. Okay, when you are given a DC voltage, you will get a DC output, where in the middle of the system you have an electric circuit. This black box electric circuit, you have a DC in and then DC out. So if you plot the waveform, you only see a continuous voltage, which is the source of the system. So you have a straight line. Because it is a receiving input of DC, the output will be DC also. So you have, if you measure input voltage and you want to measure output voltage as well, the output will be straight line also. Okay, if you plot input, if you observe current input and you want to see the effect of the black box system, the electrical circuit, you want to observe the current, so it will behave similarly, so that you will have a DC input, the output will be also DC. So if you change your system to have alternating current, we call it AC. Okay, so if you have voltage AC, like what you have now at your home, you receive a TNB supply of alternating signal 240 volts. So you will have AC, and for the frequency that this voltage given by the TNB, we have 60 hertz. Actually 60 hertz is in United States. Malaysia has 50 hertz signals. Okay, so when you have input of 50 hertz, the black box, the electrical circuits output will also have same frequency by right. However, because of physical components of the electrical circuits, the presence of capacitance, inductance, depending on the properties of the physical quantities, the electrical wiring, so it slightly changes the frequency of the output, and also the signal will pick up noise. So you will not have purely same frequency. Maybe you have slightly change frequencies, and the noise, an example of the noise, you have internet connection, sometimes it is interrupted. Sometimes the frequency of or the signal strength of your internet connection is very fast, very good. Sometimes you have, that is an example of intermittent interruption, signal interruptions. But that one detail lah, more other factors lah. But in terms of when you see input and output relationship, you will have close to when given input of 60 hertz, by right you have same 60 hertz signals output also. Okay, and then the amplitude of the signals, amplitude means the strength, magnitude. So if you have given, for example, your household source 240 volts, you will expect if the system, the electrical circuit is optimum, the output will be also at par with the magnitude of the signal. So if you have 240 input, 240 output, that means the system is having unity gain. But sometimes, depending on the electronic appliance, you do not want to have, not all electronic appliance can have can take the 240, so you can step down the signals. That is different issues lah. And if you're using 5 volts, your output should be 5 volts also. And then sometimes it involves a lot of things. You can step up, step down, and you do many things with this electrical circuit, the black box system. Okay, basically AC input, you have AC output. And this AC input, you have many different kind of waveforms. So what happens when you vary or you change the input frequency? What happens if your signal is composed of multiple frequencies? So if the first signal here is actually composition of few signals. You have the big signals and then you have small signals. So this is actually approximation of square wave signals. And this one, the second signal is sine wave. And a sine wave can be represented in terms of its mathematical function, sine omega t, where omega is the frequency of the signal. The third wave, sine 3 omega t, but divided with 3. So that means this third waveform is actually 1/3 of this sine omega t. And if you can see here, the equation for the waveform, sine 3 omega t, the frequency has triple. So you can see this third waveform is actually having 3 times the frequency of this second wave. And this one is sine 5 omega t over 5, which means 1/5 of the magnitude. And so on. The last one is sine 7 omega t over 7. This is just harmonics of these signals. Okay. Okay, now if you observe the characteristic circuits based on the frequency response, current and voltage, you want to observe the effect to the current, the input current and output voltage and output. And you can see the attenuation in terms of dB. Attenuation means how much it is truncated. Okay, you characterize the circuit based on its frequency response, and you want to see it is almost having optimum response only at certain range. So here, because this unit of y-axis in dB, dB is 20 log output over input, and 0 is actually when the log of 0 is unity gain. So here you will have a unity gain only from about 50 to about and the unit here is a logarithmic 1, 10, 100. So this is not 50. This is around I think almost few hundred, maybe 80, something like that. And from here to here, it's to about few thousands, from few hundred, few tens to about few thousands. But beyond that, the attenuation is a lot. So you have less response here prior to this range of unity gain. So when the response is flat, we have a maximum response. Prior to it, a little or insufficient response before and after the unity gain. Okay, and this is what we call it as, if you observe like this is actually similar to band pass filter. Okay, and if we all this while we consider pure resistive circuits, but in actual circuits we have impedance, where impedance comes from the reactance of the device. And in an AC steady state analysis, the frequency is assumed to have a constant frequency, such as 50 Hz. here we consider the frequency as a variable. Okay, in a DC circuit, there is no frequency. So the value of the voltage and current are fixed. Whereas in AC circuit, we will assume the frequency, either it's a constant frequency or the frequency as a variable. Okay, the magnitude, you change the frequency and you want to see the response. Okay, the magnitude of the input voltage is fixed, but then you have to see the effect of the changing frequency to the amplitude of the voltage input, because by changing the frequency, it will affect the amplitude of the signals. Okay, so the variation in impedance of basic components. Let's see what are the effect of variations of impedance, because it will give effect to the circuits. So for a resistor R, we have the impedance ZR, and you know for a resistor, the impedance of the resistor is the resistor value lah, because for ZR we have R, and we can represent impedance in terms of polar form, magnitude of the impedance and the angle of the impedance, because for impedance, the response of the impedance with frequency, it does not change. Okay, when you have a impedance, a value of Z, by changing frequency, for example, when you have a frequency of 0, frequency of 10, frequency of 100, frequency of 1000, the Z value at that different frequencies remains the same. So we say there is no change with the impedance of the resistor. Okay, so we have zero phase, zero lagging lah. Okay, but when you have an inductor in the circuit, the impedance from an inductor is actually represented by the inductance of the inductor, and ZL is actually J omega L, where when you see J is a complex number, and J omega L is equals to with angle of 90 degrees, because when you plot the magnitude of impedance and you see the response with changing frequency, there will be a phase between the impedance for this inductor, and the phase angle will be 90 degrees, and the magnitude of the impedance will be with changing frequency, the magnitude of the impedance will be higher. This is similar to the impedance of resistor, because for a resistor, the value of impedance of a resistor remains the same at different frequencies. However, the phase angle is 0. Okay, but for inductor, it is increasing, rising from 0. So if you have 0 Hertz, which is a DC signal, there is no impedance, there is no inductance. There is no impedance from the inductance. But when you have, say for example, 10 Hertz, 100 Hertz, 1000 Hertz, the impedance of the will be increasing. Okay, but for resistor, regardless of the frequency, you will have the value of impedance that comes from the value of the resistor itself. So it is a static value. Okay, and we have for impedance, inductance impedance is leading plus 90 degrees because of the equation J omega L. Because when you J omega L in terms of its polar form, it is written as omega L angle 90 degrees, and the angle is positive, meaning that it is leading. So if you leading the signals, okay, and for capacitor, when you have a capacitor, the impedance across the capacitor is given by the equation 1 over j omega c, and this 1 over j omega c in its polar form is actually 1 over omega c angle negative 90 degrees, and this negative 90 degrees meaning that it is lagging, it's behind. And if you plot the response magnitude of the impedance with the frequency, when you have a when you have a zero frequency, which is a DC supply, the impedance of a capacitor is very high. Why? Because a capacitor, you imagine it is a parallel plate. A capacitor has a very high resistance, or actually it's impedance lah. Because a parallel plate with insulator within the plates, such as air-filled capacitor parallel plates, the air gaps is introducing high resistance, which is actually constitutes to the impedance of the capacitor. But when you increase the frequency, the impedance will drop, because when you have alternating signal, when you have alternating, that means you keep on changing the polarity of the source. You switch on from positive, negative, positive, and how fast you change it, the faster you change it, the higher the frequency of it. So if you have a very high frequency, like few thousand cycles of changing on off, like positive, negative, and polarity change, it will reduce the impedance inside the capacitor. So that will make the magnitude of impedance of a capacitor drop, and it dropped from very high to very small, but the impedance itself never touch the excess. It's only infinity value, and infinitely large and infinitely small. Okay, and the response in terms of phase difference for a capacitor, the phase of it is negative 90 degrees, mean behind. So if you combine all three components in a second order system, the RLC circuit, when you have a series, so you will have combination of the impedance from the resistor, from the inductor, from the capacitor. So if you want to simplify this equation, just multiply negative j over negative j, you will produce the total impedance of this series RLC circuit is actually omega RC plus j omega squared LC minus 1 divided by omega C. Okay, and the magnitude of the impedance is actually square root of omega RC squared plus 1 minus omega squared LC divided with omega c. And in terms of magnitude of the impedance, the small frequency response, you will have the effect of capacitor is pronounced in a smaller frequency range, but at higher frequency range, you will see the effect of inductance. So that you will have a small decreasing impedance, but then rising almost linearly with the increase of frequency. And for the phase difference is observed from voltage and current. Okay, and here you will see at lower frequency, you will see the phase difference from -90 because of the effect of capacitor, and then rising to almost a value close to 90 degrees, because this 90 degrees is actually the effect of inductance. Okay, and this phase difference is polar value, angle Z equivalent equals to, you can find as tangent inverse of the component here, omega squared LC minus 1 over omega RC. But the magnitude is the square root of omega RC squared plus 1 minus omega squared LC divided with omega C. Okay. If we observe at specific components, this previous one, if you observe only at the capacitor, the frequency dependent behavior of series RLC circuit, we have to differentiate the behavior of series RLC and parallel RLC. They produce a slightly different behavior. And for a series, similar to what I have presented just now, so total Z for the circuit is this equation where you have the impedance from resistor, inductor, and capacitor. And we don't like the omega, the J, so you can change J omega with another variable. So let's use S, and this S, why we use S? Because we want to represent it as a transfer function, and when you see J omega, you replace it with S, so that can make the equation of the impedance of the system S is equals to S squared LC plus SRC plus 1 divided by SC. So in this case, the equation looks nicer lah, no more J, no more omega, but actually they are the same. Alright, and okay, so in terms of transfer function, as I mentioned in this chapter, our main concern is to represent a system in terms of its transfer functions. So one useful way to analyze the frequency response of a circuit is the concept of the transfer function, H omega. It is the frequency dependent ratio of a force function, Y omega, to the forcing function. Force function means the input. Forcing function means the output. I'm sorry, opposite. Forcing function, X. Forced function is the Y. Y is the output. X is the input. And you consider the black box is a linear network. And this linear network can be represented as its transfer function, H omega. H omega or Hs. So a transfer function can be represented as the relationship between the output and its input. So therefore we have H omega is equals to Y omega over X omega, the output divided with the input, which is actually the gain. Okay, a gain of a system is always the ratio of output to input. So the transfer function is actually the gain equation. All right, and there are four possible types of transfer function. We can always have, if you want to observe the relationship in terms of voltage gain, so you consider VO over Vin. If you want to consider current gain, you will look at the ratio of IO to In. If you want to combine, you want to observe V output as the effect of changing input current, which is VO over In, and we call this ratio as a transfer impedance. If you want to observe current output with the effect of changing voltage input, or with the ratio of IO over VI, you will have this transfer function known as transfer admittance. So these four categories can be a voltage gain, current gain, transfer impedance, or transfer admittance. Okay, because you are only observing current and voltage, but having the two current at the input side, you have current and voltage. At the output side also, you will have current and output. In the second part of my lectures later on, the body plot, the two-port system. Two-port system, we will also evaluate in terms of input and output relationship. Okay, so in any system, at the input side, there is always current and voltage, both at the input and the output sides. So with that combination of input and output, you will have four types of transfer functions. So in terms of the equations or the symbol or abbreviation, when you have input voltage, voltage gain is always, we call it G. G is a standard form for gain equation. GV means voltage gain. GI means current gain. But for transfer impedance, we call it ZS. And transfer admittance is YS. Because you represent admittance as Y, you represent impedance as Z. Admittance is how much you allow a quantity to pass through. Impedance is how much opposition or the resistance of it, and you call it as Z. All right. So these are the four values. Okay, an example. Okay, you have a circuit, a simple circuit. Given the transfer function which relates the output VO over VS and its frequency response, let's have the VS equals to Vm cosine of omega t. Here you see the source Vs is equal to Vm. Vm means the magnitude, and cosine omega t, cosine, the maximum value is 1. The minimum is -1, because a cosine function, it always vary from -1 to 1. But because of the multiplier Vm in front of the cosine function, this will determine the actual magnitude. Okay, so if you have 100, the maximum of the Vs will be 100 lah, and the minimum will be negative 100, because cosine value will be maximum 1, minimum negative 1. Okay, and here you have V source, resistor, and capacitor, and you are given VO is measured across the capacitor. So let's write the transfer function of the system. We have H omega is VO over Vs, which is actually, you can write for this part, the value is 1 over J omega S. And R plus 1 over J omega C. The V source is this bottom part of the equation. So therefore you will have H omega is equals to 1 over, if you divide everybody with, and you can simplify it into, divide everybody with J omega C, you will have 1 over 1 plus J omega RC at the bottom. And H is equals to 1 over 1 plus omega over omega naught squared. And the phase angle between current and voltage, you will have negative tangent or inverse of omega over omega naught. The magnitude plot is from 1 to infinity, and omega naught is the resonant value at which 0.707, which is 70% of the maximum 1, is considered the value of 1 over RC. And for the phase response, at omega naught here, you will have the response of negative 45 degrees, half of the maximum phase difference. Okay. And for another example, this will be the same. I think page. Okay, if you have for this for inductor, similar to the capacitor, but now the difference is inductor behaves increasing impedance, whereas capacitor decreasing with the slope. Okay, so for the transfer function, H omega equals to VO over Vs, where VO is J omega L and the Vs is R plus J omega L, and overall you will have omega naught is equals to R over L. Okay, and therefore your H magnitude of this transfer function is omega over omega naught divided with 1 square root of 1 plus omega over omega naught squared. And the phase angle is H omega is pi over 2, half of pi over 2 minus tangent inverse of omega over omega naught. So as omega is at omega equals to 0, H equal to 0. As omega increase to infinity, H will be approaching 1. Okay, phase angle at omega 0 is 90. Phase angle as omega is approaching the infinity, it becoming 0. And at omega equals to resonant frequency, H is equal to half of 1 over square root of 2. And this 1 over square root of 2 is actually 0.001. 707 or 70% of the magnitude. And phase angle will be 90 degrees minus 45, which is at 45 degrees. So if you see the magnitude response is increasing to 1, whereas the phase angle from positive 90 decreasing to 0. And at omega naught, which the resonant frequency, R over L, the phase angle is 45, but the magnitude here is about 70.7% of maximum value. So if you compare with the capacitance, your capacitance at resonant value, omega naught, is 1 over RC, but for inductor, LC value. Sorry, R over L. Okay, and then now we want to discuss on zeros and poles. Yes?
I want to ask about the last example, 14.1. How to change the H omega to H by modulus? How get the cert 1 plus kurungan W over W naught tu? Yang sebelum lagi.
Which one?
Praktis sebelum ni. Yang satu lagi.
Oh, 14.1.
Example.
Okay.
This one, H omega ke H. Macam mana dia boleh dapat cert 1 plus omega over omega naught yang bawah tu. Yang tu.
This is the magnitude.
How to get the magnitude?
Magnitude is simply, this is a calculation from, normally when you have this value 1 over 1 plus j omega RC. You refer to textbook. This is the values, right? You guys have the book or you have only online book? Online book, right? You can look at the book, and this one is actually a standard way, standard form to calculate. When you have 1 plus j omega, and the magnitude is taken as 1 over square root of 1 plus omega over omega naught squared lah. That is the value.
So kalau memang standard lah, kalau jumpa 1 plus j omega RC, kita tukar pada 1 plus yang ada j omega, kita akan ubah pada omega over omega naught lah, kiranya macam tu.
Yes. Kalau tengok yang practice problem ni pun sama juga. Omega over omega naught squared. The magnitude is the standard way to calculate it.
Okay, kita dapat ni.
And sometimes this notation is just written for the sake of mathematical representation. But in circuit analysis, you don't have to evaluate the values in your calculator pun. This is just a mathematical representation sahaja. Okay. Don't worry too much about it. This is just expression mathematically lah. And where are we? Okay, now we move on to the zeros and poles. Hold on. Okay, zeros and poles. To obtain the transfer function H omega, we first convert the frequency domain equivalent components in the circuit. And how can we express H omega? Is simply you can express it in terms of numerator divided by the denominator, because the transfer function is always the ratio of output to input. So the output will be the equation n omega. The input is the denominator equation expression d omega. Okay, so the n omega and d omega are most of the time the polynomials expression. So h omega is the equation of the transfer function. So the zeros are where the transfer function goes to 0. Poles are where it goes to infinity. Okay, so they can be related to the roots of the numerator and the denominator. So zeros is the solution for the numerator. Poles are the solution to the polynomials of the denominator. So example, calculate the gain IO over IS and its poles and zeros. Okay, so here you have a circuit of 4 ohms, 2 Henry, and 0.5 farad. So capacitor, inductor, and then you have a current source here, and you have current output. Okay, the question asks you to calculate the gain IO over IS. So you have a transfer function of current transfer function IO over IS, and you want to evaluate the poles and zeros for the transfer from the transfer function. So you must write the equation of IO. Okay, so here you have IO is output at this capacitor, and IO is actually because you have 2 Henry here, 4 plus J2 omega divided with 4 plus J omega, which is this section, plus 1 over J 0.5. Because this one is actually current branches, total current branches here. Current passing through here is only 4 plus J2 omega. But current that pass through this I input is the combination of current that pass through the middle branch and this branch. So that you will have this current divided by this branch plus the other branch. Okay, and if you simplify this one, and okay, don't forget that IO is this part multiplied by this part, because IO over II is only this. And you will have, if you simplify the equation and you bring down II over to the left side, you will get this value, and you simplify it. You substitute S omega with J omega. You will produce, this one is S plus 2 times S, and S squared plus 2S plus 1 at the bottom. Okay, so now you have numerator and denominator. So the numerator will give you the zeros value. The zeros are at s and s plus 2 equals to 0. When s values gives this expression 0, that is the value of the zeros. So what values that can give zeros? So when s is 0, 0 times 0 will give you 0. When s is negative 2, so negative 2 times 0 becomes 0 juga. So in other words, the solution to this expression is the zeros values. So that you will have two zeros from this numerical expression. You will have Z1 is at S equals to 0 and at Z2 equals to negative 2. So you say the zeros are at negative 2 and at 0. For the poles is taken from the denominators, where the denominator is having expression of S2 plus 2S plus 1. Okay, so you can simplify this. S2 plus 2S plus 1 is equals to S plus 1 squared. So when S is equal to negative 1 plus 1 is 0. 0 squared is 0 lah. So you have double value. S at negative 1 is the poles to the transfer function. So here you have double pole. Okay, then if you do practice problem 14.2, you can explore more on the poles and zeros of a transfer function. Okay, then decibel scale. A decibel scale is a scale that is used to describe transfer frequency response. We will use, when you say frequency response, we always do a graphical representation of the system in terms of the body plot. Okay, and these body plots are actually a logarithmic scales. Logarithmic scale, why we do logarithmic scale? Because it's a power of 10. Frequency can change from small frequency to 1000 to mega, power of megahertz, gigahertz. So if you use linear scale, it would be difficult to graph it. So the best is you use a logarithmic scale where we consider power of 10. So that the scale of the frequency is shorter. Okay, and the transfer function, which is an expression of the gain of the system. Gain is expressed in the log form, is typically expressed in bells, or more commonly decibels. Deci means 1/10. Deci of a bell. And the gain in dB, decibel, dB represents decibels, or a short form of decibels. And GdB is equals to 10 log 10 of the output over input, P2 over P1. P2 is the amplitude. And one problem with the transfer function is that it needs to cover a large range of frequency. Okay, plotting the frequency response on a semi-log paper makes the task easier, where the x-axis is plotted in log form because the x-axis is the frequency and the y-axis is the magnitude in linear scale. And these plots are referred as body plots. And the body plots either show magnitude in decibels or the phase. in the degrees as a function of frequency. So there are two parts of body plots, magnitude plots and phase plots. Magnitude plots represents the gain, whereas the phase plots represents the shifting of phase angle between voltage and current. Okay, and the standard form, the transfer function may be written in terms of factors with real and imaginary parts. For example, and this is again H omega equals to K. These are just mathematical expression in the standard form, where you have K as a multiplier, K J omega plus minus 1 and 1 plus J omega. 1 plus J omega is the zeros, gives the information regarding the zeros because it is in the numerator of the equation. 1 plus J omega over P1 multiplied by 1 plus J2 eta omega over omega naught omega n. And the bottom here we have over P1, which indicates the poles, as it is actually information regarding the poles. You put Z1 at the top because it gives you the zeros for the transfer function. Okay, and this standard form may include the following 7 factors in various combinations, where again K, you have here K is the gain, a pole J omega negative 1. J omega negative 1 means at the bottom. Power of negative 1 is in the bottom of a fraction equation. Okay, a simple pole gives you 1 over 1 plus J omega over P1, or a simple 0, 1 plus J omega over Z1. A quadratic pole where you have 1 plus J2 eta squared eta 2 omega plus J omega, and or this one. So you have equation of S squared plus S plus a constant number. Okay, when you have a power of 2, that means a quadratic pole. Okay, and normally poles as it is present in the bottom of the transfer function. And this is the expression written as a mathematical equation. Okay, and we can always evaluate in terms of graphical also. In a body plot, each of these factors is plotted separately and then added graphically. Okay, the gain K, the magnitude is 20 log 10 of K, and the phase is 0 degrees. Both are constant with frequencies. Okay, the K is constant. Only the zeros and poles are changing. So pole on 0 at the origins. For the zeros, J omega, the slope in magnitude is 20 dB per decade, and the phase is 90 degrees. For the poles, J omega power of negative 1, the slope is magnitude of negative 20 dB per decade, and the phase is negative 90 degrees. So these are the 7 characteristics: gain K, poles, simple pole, quadratic poles, and then gain K is written as 20 log 10 of K, and the changing slope of the poles and 0. 0 is positive, 20 per decade, 20 dB per decade, whereas poles is negative 20 dB per decade. And the phase angle negative for the poles, positive for the zeros. You might be confused. You may not understand what I'm talking about. Maybe not even 10% of what I'm describing now. You will understand later when we evaluate, when I show you the example of how we evaluate a body plot, how we sketch a body plot from a transfer function, because it is important. And the body plots, continuation of the body plots for simple poles of 0. For the simple zeros, the magnitude is 20 log 10, 1 plus j omega over z1, and the phase is tangent inverse of omega over the zeros value, where the parts of the transfer function h dB, h magnitude of the transfer function is always 20 log 10, 1 plus j omega z1, that will give you 20 log 10 of omega over z1. And this can be approximated as a flat line and a slope line that intersect at the zeros. So there will be the zeros and poles then become a cut-off frequency. Cut-off or the turning point. We call it turning point. Cut-off frequency more reference to a filter circuit. So here we call it turning point. So the zeros and the poles become the turning points or the break frequency. Okay, and the phase can be plotted as a series straight lines from omega equals to 0 to omega less than the cutoff frequency z1 over 10 if we let phase angle equal to 0. At omega equals to z1, we let the phase angle equals to 45. For omega more than 10 times the zeros, we let the phase angle equals to 90. So these are actually, when you plot a section, you always use the range of the frequency from 1 to the 10th. So that's why here you have, actually you have to have the middle 1/10 lower, a 10th higher. So you have to use 2 decades, 2 decades change. And the pole is similar, except that the corner is at omega equals to the poles value. P stand up for the poles, Z stand for the zeros. And the poles always have a negative slope. Simple slope is having 20 dB per decade. If a pole, negative 20 dB per decade. For double pole or double zeros, it becomes 2 times 20 becomes 40 dB per decade. Okay. For the quadratic here, we have 40. Quadratic means doubles. Quadratic poles or zeros, the magnitude of the quadratic poles because of the power of 2. And you multiply, bring the 2 in a log function. 2 is put in front of the log function. So 2 times negative 20, you get negative 40. Thus the magnitude plot will be 2 lines. One with slope 0 for omega less than omega n, and the other slope with slope negative 40 dB per decade with omega n as the corner frequencies. So these descriptions are summary of what you have to do when you want to plot a body, when you want to evaluate a system, an electrical system in terms of its body plots. And the body plots, the phase can be expressed as phase angle equals to tangent inverse of the numerator over denominator, and we will have 3 different sections: 0 at omega n and at omega approaching infinity. So there are only 3 sections, 0, 190 degrees and 180 degrees. Maximum is 180 degrees. Okay, and this will be a straight line with a slope of negative 90 degrees, starting at omega n over 10 and ending at 10th omega n. In the middle is no multiplier, so you will have 3 sections of it. And for the quartic zeros, the plots are inverted. Okay, in terms of the diagram, summary of the 7 characteristics, and here you have K from constant. You will have magnitude plot of straight lines. Omega is actually the frequency. Okay, and 20 log 10 of K is a straight line. Okay, and then the phase is straight at 0. For zeros, j omega to the power of n, you will have at a turning frequency, turning if it is at 1, then it cut across, and the slope, if you start here at 1, you find for 10, when magnitude is 10, when frequency is 10, so the amplitude here will be 20. So then you will get a slope of 20 dB, and the scale in the y-axis as dB unit. So then you will get a 20 dB per decade for the zeros part. But for the phase angle, it is a straight line at 90 degrees, positive 90 degrees. For poles, you have a negative slope of 20 n dB per decade. And the phase angle for the poles is negative 90 degrees. Okay. When you have an expression 1 plus j omega over z, you will have a flat line at the z value, at the turning point. It will increase with a slope of 20 dB per decade. But for the phase angle, it is flat when it reaches the turning point. And the turning point, actually you can see turning point 1/10 before it reaches, z is in the middle here. So it starts to rise 1/10 of the z value. It rises until 10 times z, and then it becomes flat again, but it flats at 90 degrees. That is for zeros with an expression of 1 plus the zeros part. For the poles, similarly, when you have an expression of 1 over 1 plus j omega over p, it will become flat prior to the turning point P, and then it becomes flat. It goes down with a negative 20 dB per decade. So similar to the zeros, flat at 0, and then start to go down at 1/10 of the P value at the cut of the turning point poles until 10 times, and then it is flat at negative 90 degrees. So for the quadratic poles, the difference is only the slope lah. Instead of having 20 dB, you have 40 dB slope. Same for zeros and poles. But the behavior is similar. For the quadratic or double pole, you have it span from 0 to 180. But for simple poles and zero, it spans from 0 to 90 degrees only. So the only difference is the range. Okay, now we go with example. what I have been talking about, the changing, you will not see it until we sketch magnitude and body plot of a transfer functions. So for example, sketch the magnitude characteristics of this transfer function G j omega is equals to 100, 0.02 j omega plus 1 divided with j omega squared. So you are given the transfer function G j omega and sketch the transfer function in terms of its body plot. So body plots consist of two parts, the magnitude plot and the phase plot. So this graph is semi-log. This one is both log and log. Y-axis is also log. The x-axis is also log lah, because it's a frequency, so you need to spend. And so the top part we designate it for magnitude plot. The bottom part we designate it for phase plot. So we have angle. The top part is magnitude. So we span from 40 dB to -20. And here you will see the scale of the y-axis is linear. This is linear, 0, 20, 40. But linear of dB, yeah. Okay. What are the zeros? When you have a transfer function, you have to be critical to know what are the transfer functions components, the poles and the zeros. So the numerator gives the zeros information, the denominator gives poles information. So from the zeros and poles, it gives you indication of what is the magnitude plot and the phase plots. So let's transform it into a standard form. Standard form is the form that is in the mathematical expression tadi, yang banyak-banyak, yang ada j omega, yang over z over p and so on. Why we put it over z over p? Because you want to make it easier for you to identify what are the zeros, what are the poles. So when you transform it this way, 100 times 0.02 j omega, it's difficult for you to know what are the value of the z. So you make it over z. So to make it over z, you rearrange the numerator expression. And okay, 0.02 is simply over 50 lah. And from here you know Z1 is 50. The poles j omega and with the p value at constant. Okay, it is now when you change this manner, you will have now have the expression of the transfer function is in the standard form with a break at 50, which means z value is 50, and double pole at the origin because you have j omega squared. So in other words, if you replace it with s, you have 100 s over 50 plus 1 divided with s squared. So the s squared at the bottom gives you the poles, and the poles at the origin. Origin means at 0 lah, and double poles. But the zeros at 50. So now you know 50 is the break point or the turning point for the slope of line of the transfer function. And you identify here 100 and this j omega. You also identify j omega over 50 plus 1. Then you identify at 10 here. Okay. You know the magnitude, the phase from the phase angle at 0 here. You have this line is almost 90 degrees and 180, and here you identify 50. This is 110, so this is 50, and you identify 50 here and 500. This is 500. And the K value gives you at this line. It cuts at 40 when frequency at 1. And this line from 10 to 50, straight line, and then rise by 20 dB per decade. So because it's at 50, so you find 500, 0 to 20. So the line is not that accurate, but it's actually meant for 20 dB per decade. So this part is actually for the numerator part, j omega over 50 plus 1. And the phase angle for that part is flat line at 90 degrees. And you identify from 50, flat and then flat. Rise and then flat at 90s. So prior to this one, 5, because 50 is the center, 500. So flat prior to 5, and then slope of 20 dB, not 20, 90 degrees. The slope is actually 90 to 90 is 45 degrees per decade. 45 degrees per decade. For double pole or the quadratic is 90 degrees per decade. And once each term is drawn, we then form the composite. Composite means combination of partial parts of the phase magnitude plots. So this part, the dotted green, a drop here is from the K value, and then this part combined with the 0 part remains as the line that drops, but between 5 it drops slightly. Okay, the red green here, and so you don't see that much of drop here. It's drop here, so quite difficult to see. I have another example. So this line is negative 40 decade, double pulse through the origin. Origin means at 0 here, 50 corner frequency plus 20 dB decade. So the overall, the dotted lines are the final value of the sketches. Here you have 40, here you have 20. So you have the final part is negative 20 dB. So the line here dropped from 40 dB sampailah 50, and then the slope becomes small, like to 20 dB, drop to 20, only negative 20 dB per decade. And these are the sketch for this transfer function. Okay. Another example, maybe this one is more easier to understand. Given a transfer function of g j omega equals to 10 j omega over j omega plus 1 times j omega plus 10. Here obviously you have two poles, one zeros, because the numerator has only one expression, the denominator have two expressions. However, this is not in the standard form. The standard form is always j omega over z in the numerator, in the bottom, in the denominator, let j omega over p1, j omega over p2, so that it's easier for you to identify the corner frequency or the turning frequency. But here you know, you want to make this j omega over 10 because the standard form is always j omega over p plus 1. Here you have j omega over 1 plus 1, but this one j omega over 10 plus 1. But when you introduce over 10 at the bottom, you have to, it has to be reflected also in the numerator, because you have to multiply top and bottom with 1 over 10. Okay, put it in standard form, then you will have j omega over j omega in the numerator divided with j omega plus 1 times j omega over 10 plus 1. So you know, obviously the zeros is at having 1 0 at the origin, whereas the poles is at 1 and at 10. And here we have the graph. Bottom is for phase plot, top is for magnitude plot, and j omega gives zeros through the origin, so it must run through 1 and slope of 20 dB per decade. So if you take 0.1 to 10, so it must span from negative 20 to positive 20, because and from here, from negative 20 to 0 is 20 dB per decade. From 0.1 to 1 is 1 decade. From 1 to 10 is another decade. So the increment of the x-axis is per decade, a decade. 1, 10, 100, 1000, and so on. And the span of the value of the x-axis should be sufficiently, because you can sketch 0.1, 0.01, 0.0001. So how much scale you want to use? It depends on the highest. Normally we take at least 1 decade smaller than the smallest break frequency, and 1 decade bigger than the biggest break frequency from this transfer function. So here you have the break frequency at 10. So 100 should be sufficient. And because we have the zeros at origin 1, so the 0.1 should be sufficient. So your graph should span from 0.1 to about 100. If you have 0.1 to 1000, it's okay also. But sometimes if the frequency is too large, you cannot plot. The scale will become too large, so it is difficult for you to plot precisely. So that's why identifying the sufficient range is good, so that you have the graph is not too small and it's not insufficiently enough for you to sketch. Okay, here is the line of running through the origin with a slope of 20 dB, which is obtained from the zeros equation, from the numerator of the transfer function. And then the phase for these zeros is going to be flat at 90 degrees, positive 90 degrees. For the poles, there are two poles at turning point one pole equal to 1. So here, prior to the pole is a straight line, but then when above than the pole, above than the turning point of the first pole, it drops by negative 20 dB because it's a simple pole. It's not a double. It's not a quadratic pole. So then you will have from 1 to 10, it drops 20 dB. 20 dB per decade. Okay, and the second pole 10. And here is from the phase plot. The phase plot is running through the corner frequency 110 and 10 times, and the slope of 45 degrees per decade, which is from negative 0. Here is 90, and here is 90. Okay, and at that the frequency is flat again. For the second pole, let me okay, the second pole, okay, 0 until it reaches the corner frequency of 10. Then it goes down. For the phase plot, it runs through the corner frequency, span from 1, which is 1/10 of corner 10, and 10 times at 100. So from 45 to with 45 degrees per dB, the slope of this phase plot. So flat prior to that one, and then flat above and it. Then you need to combine. Once you have there are 3 terms here. One term from the zeros, 2 terms from the poles. So when you combine them, you get the dotted green line. Here you have 0 plus the 20 dB, you obtain 20 dB per decade line. But from 1 until 10, you have 3 parts. 1 rising, 1 falling, same slope. This is rising 20 dB per decade. This is falling 20 dB per decade plus 0 slope. So when you combine all 3, you will get 0 slope. So at this part, the magnetic plot becomes flat lah. But this part, here you have three parts also. One rising 20 dB, one falling 20 dB, another falling 20 dB. So at this part, plus 20, negative 20, negative 20. So the result is negative 20. So then you will have a falling of 20 dB per decade. So therefore, the dotted green lines here is the magnetic plot of this transfer function. For the phase plot, you combine them, this line plus the 90 degrees plus the 0. So this one, the line negative 45 dB per decade from 0.1 to 1 here is elevated a little bit because of this 90 degrees line. And from 1 to 10, so 90, and here is negative, negative. So it becomes double lah. So then you see a drop more. And but this one, you have only one line of negative 45 dB per decade, negative 45 degrees. So that this part become less, the slope become less. But you will see the line is actually like a curve lah. So altogether, you will have the magnitude and the phase plot. Another example. Okay, I do a lot of examples so that you can see what is going on and how we can plot. Sketch the magnitude characteristics of a transfer function with g j omega equals to 10 to the power of 4 j omega plus 10, j omega plus 2, and in the bottom we have j omega plus 10, j omega plus 100. So here you see it is not in the standard form. You can change into the standard form, but you see there are three parts of it. Four lah. One is K, zeros the poles, two poles at the bottom, 1 0 from the numerator. Here you know straight away you can see 2, 10, 100 as the break or the corner frequency. When you put it in standard form, you divide by 10, divide by 10, divide by 100. That means you multiply 1 over 10, 1 over 100, top and bottom. And at the bottom here, you want to divide with 20, with 2 at the top. You multiply 1 over 2. So you introduce 1 over 2 at the numerator. You must also introduce 1 over 2 at the bottom. And that will give you 20 j omega over 2 plus 1, j omega over 10 plus 1, j omega over 100 plus 1. So now everybody is in the standard form. Okay. Here you see the lowest value is 10, 100, 0.1 and 1000. 0.1, 1, 10, 100, 1000. At least 4 lah. You can plot 1 as the lowest range. 1, 10, 100, 1000. Here will be 10,000. And the span is from 20 to 40 dB. Negative 20 to 40 dB. Okay, the 20 is from the K value constant. And 20 log 20 dB will give you 25 dB. And for the constant K here, the phase plot will be flat at 0. For the second part of the zeros, the j omega over 2 plus 1 here, you will have a cut off or the corner frequency at 2. So at 2 will be somewhere here. So you identify 2 and 20. So prior to 2, it is flat line at 0. From 2 to 20, it will rise by 20 dB per decade. So the phase plot, it runs through 2. So you would expect 0.1 dekat sini. So that's why I think 0.1, if you plot 0.1, is more accurate because you can plot, you can span the line prior to that is 0. Okay, and above this one is at 90 degrees. Okay. For the poles, j omega over 10 plus 1, you will get identify 10, 0 prior to corner 10. And then because it's 0, it will drop by 20 degree per decade. So you draw a line 10 to 100 and drop off 20 dB. So 0 to 20. The phase plot, it runs to 10. So prior to this one is flat. Above that one is flat again. Okay. For the last poles, j omega over 100 plus 1. So your corner is 100. So prior to 100 is a straight line, flat at 0. And then it will rise from 100 to 1000. And not rise, or falling because it's a pole. So it drops by 20 degrees per decade. The phase plot is run through 100. 0 prior to 10. And 90 degrees, negative 90, above than 1000. For the K, now we do the composite. So this straight line at 25 here is from the K value. 20 log of 20, you will obtain, you plug in your calculator, you will obtain 25 dB. And here you see, because here you have all 4, 1, 2, 3, 4 parts. Straight line, rising, 2 falling. So if you combine plus 25 plus 0 everybody, so you will get plus 25 lah. And this part, 1 rising, so this one will be elevated because the other 2 lines is straight at 0. So this line will be elevated. So you bring this line to the top, above the 25. But from 10, we have to cut from 10 and then, okay, from 10, here you have 1, 2. So here will be cancelled. So it will be flat. And from 100 and above, you have 2 drop of 20, 1 rising. So the effect will be drop from 100 line. So you will see straight line prior to 2 and then rising until 40 and then flat until 100. For the phase plot, you do the same, you combine all together. And you will have, because of this line elevated, so this one will be elevated a bit. But this one, because you have 1, 2, so it drops by 1. And because here you have two drops, -20, so it becomes drop. And at this part, less drop. And so the overall will be a curve line. Okay, so much about it. Plotting. I think if you look at the UKM folio, I have posted few series of videos which I found from the internet, YouTube, of lectures by other lecturers, which I think is very useful on how you can do the plotting of body plot, the magnitude and the phase plot. Please watch the videos so that you can have a better understanding of how you should be able to plot manually. Okay, this body plot is very important for frequency response. But when you do your mini project, you can present the output in terms of simulation plot and also manual plot. Manual plot is for you all to experience the actual plotting. Okay. Now we move on to an example from the Alexander book, example 14.3. Okay. Given a transfer function, construct the body plots for this transfer function. Okay, you can put it in standard form, 200 j omega over 2 plus 1, so that you rearrange it so that you will have j omega over p, j omega plus 1, j omega over p1 plus 1, the second term, j omega over p2 plus 1 also. Okay, and then okay, after you put the standard form, you will get 10 j omega 1 plus j omega 2 1 plus j omega over 10. It's the same thing, j omega over 2 plus 1 or 1 plus, you put 1 in front, they are the same thing. Okay, and the magnitude form, this is just expression. Okay, again expression. 10, no need for you to calculate the magnitude, whatever, just write in terms of mathematical representation of the equation. 10 j omega 1 plus j omega over 2 and then 1 plus j omega over 10, and the phase angle will be 90 degrees minus tangent inverse. So 90 degrees means you start from 90 degrees and minus tangent inverse omega over 10. So step 2 is identify the magnitude and the phase. So the magnitude is 20 log 10 of 10 plus 20 log 10 of j omega minus 20 log 10 1 over j omega over 2 minus 20 log 10 1 over j omega over. This is again mathematical expression. So what the important thing is you should be able to sketch it. And in terms of the phase angle, the mathematical expression is always 90 degrees minus tangent inverse of omega over 2 from the poles minus tangent inverse omega over 10, the second pole. Okay, the third step is to sketch. Okay, sketching you can do. This part is for the first. Okay, the line that runs through 20 dB here is from the K function 20 log 10 of 10. Okay, and this line is the one that from the second zeros. and which actually at 2, it should be 0 until reaching 2, then it rise. Okay, but the other two lines that drops falls at 2 and 10. The lines prior to 2 and then it drops. Prior to 10, it's 0, and then it drops. And zeros at 0 here, it runs through the origin. Wherever it runs through the origin, it must straight line, a slope of straight lines run across the origin. Origin is at 1. And this is for the magnitude plot. So altogether, when you combine this, 20 plus this line plus this line, all 4 lines together, you will produce elevated line that runs to the origin until 2. And from 2 until 10, because we have 2 and 10 corner frequencies, from 2 until 10, there will be 20 positive, 1 positive, 1 negative. So this one, there is no slope lah, 0 slope. So the line will be flat. But from here, because there are 2 negative lines and 1 positive line, so it will drop, will give you 1 effect of 1 negative line. So therefore, you will have rising from here until 2, and then flat, and then drop by 20 degrees until the end of the world. So this will be the magnitude plot for the equation given. As for the phase plot, you identify the lines, the origin 1, it will run through 90 degrees, and then at 20, at 1, at 2, and at 10. Then you combine them together, you will produce a line of straight from the 90s, drop, because there is only 1 drop, and then 2 drops here, you will drop until 20. Then from 20 to 100 here, there is only 1 line, because from here, the line is flat again, so leaving only 1 negative slope. So therefore, here, the slope less by less by 45 degrees per decade. So therefore, you will have many turns in the phase plots of the transfer function. Drop, and then more drop, and then less drop, and then flat. So there will, it becomes, as an overall, it becomes a curve of the phase plots. Okay, last one, practice problem 14.3. Draw the body plots for the transfer function. H omega equals to 5 j omega plus 2 j omega times j omega plus 10. So here you will see change to the standard form. Introduced, you want to make it 1 and j over divided by the 2. So you multiply by 2 at the bottom here, and then you will produce an overall of j omega over 2 plus 1, j omega over 10 plus 1. So then you see the 0 will be 2, the poles will be origin and 10. 0 at 2, poles at origin and 10. Then you sketch the body plots. So to sketch the body plots, you can plot 1 by 1. And the red line is going to be the final composite plots. For the phase angle, you do the same. And I think this one you can try on your own to plot. Take a a blank paper, then identify the, make sure you use logarithmic scale. Okay, so it's 11 o'clock already. I stop here. Okay, here you see the poles. Before, I have some animation here. For the poles, for the magnitude and phase plot. So this, the straight line, the red straight lines will be the phase plots and the magnitude plots. Another example. Okay, sometimes if you are given a transfer function, you need to sketch. Sometimes you are given the transfer function sketch, the magnitude plot, you need to do the reverse. Obtain the transfer function from a body plot. So you should be able to plot, you should be able to obtain the transfer function. For example, here we have given many turn points, then you need to convert. So this is not that difficult. You have to identify the turning point, corner frequency. So here you see 1, 5, 20 as the turning points. But from the turning points, you do not know whether it is a 0 or a pole. But there is clue for it lah. So the first step, you identify the corner frequencies, 1, 5 zeros, and identify which are those, whether they are poles or 0. And if you see logically, at this point, change from rising to flat. So it must be negative lah. Add with something negative, then it should be a poles. From here, the second turning point is 5, drop more. So this must be also a poles. At this point, drop again. So 20 corner must be another pole. So there are 3 poles here. But then you have start at 40. So it must have a K value. 0 must be at the origin. So you have 40 equals to 20 log 10 of K. So from this 40, you will obtain K value, where K should be 100. Okay. So P equals to 1 will give 1 over 1 plus j omega over 1. Corner of 5, 1 over 1 plus j omega over 5. Corner of 20, 1 over 1 plus j omega over 20. And the overall equation should be 100 j omega, 1 plus j omega over 1, the first corner. The second corner gives you 1 plus j omega over 5. The third corner, 20 here, 1 plus j omega over 20. So altogether, if you rearrange, make it beautiful, you will get j omega times 10 to the power 4, j omega plus 1, j omega plus 5, j omega plus 20. This is the transfer function for this sketch of magnitude plot. Okay. The last one, another example of obtaining the transfer function from a sketch of magnitude plot. Find the transfer function for this plot. Here you see 2, 20, and 100 as the corner. But you must identify whether it's zeros or poles. So 2, because it's from flat until it rises. So this must be zeros. It cannot be poles, because if poles, it must drop, whether it flat or it drops. So here 2 is zeros, 20 is pole, 100 is pole. So then 20 is the K value. 20 equals to 20 log 10 of K. From here, K becomes 10. But this part from 2 to 20, you have increase of plus 20 dB per decade. So you will have the portion of this section is 1 plus j omega over 2. Okay. For the cut off at 20, you have negative 20 dB per decade. That part it gives you 1 plus j omega over 20. And the last corner, negative 20 dB per decade at omega over 100, which gives you an expression of 1 over 1 plus j omega over 100. So therefore, altogether, you put everything together, you will get 10, 1 plus j omega over 2, 1 plus j omega over 20, 1 plus j omega over 100. Make it beautiful, you get 10 to the power of 10 to the power of 4, 2 plus j omega, 20 in the numerator, 20 plus j omega, 100 plus j omega. So I will stop there. And the next class, next week, we will discuss more on other parts. So enough for today. You have been dealing with body plots. Something new. Please watch the videos so that you can be familiar. Okay, so I think that's all for today. I will stop presenting. And so thank you guys. Any question? Hope you can understand. Maybe it's difficult the first time for you all come across how to sketch a body plot, how to sketch a transfer function into a body plot. So this is how you can plot nah. So if you don't have any questions, I shall let you all go. So thank you guys for paying attention from the beginning until the end. Until we meet again next week.
Thank you, Doctor.
Thank you, Doctor.
Okay. Assalamualaikum.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.